Hello CTM students and welcome to chapter 14. This is 14.1. We are starting our discussion of graph theory, and so we're going to be talking about something that's probably a very new type of math or a new branch of mathematics for most of you. Some of it was new for me. I'm just learning some of this stuff right before I'm teaching it, just being honest with you, and so kind of teaching myself, and I'm going too fast here. I wanted to mention before I get to the actual notes that there are some definite real-life applications to graph theory. If you've seen subway schematics like this before, this is an application of graph theory where we have these nodes or vertices and we have these edges or these lines connecting them. This is actually the metro system for LA, and you've got here, it looks like Jackson Hole, Wyoming, very close to the Grand Tetons, beautiful skiing city right there. Excuse me, this is an application of graph theory here as well, where we've got all these airline flights departing and leaving from all these, or departing and arriving in all these different cities. We're going to see more about this and how there are a ton of applications to graph theory. But let's get started now. 14.1, graphs, paths, and circuits. There's going to be a lot of new vocabulary here. You'll want to make sure you're paying close attention so that you got the foundation for the rest of the chapter down with this lesson here. So here's some examples, or this is an example, singular example of a graph. Now, we've drawn graphs before. There's different types of graphs. The graph here is probably different than what you're used to seeing. Graph, maybe before what you thought with math would be like the Cartesian plane or the coordinate plane, where you'd have a graph drawn on there with an equation. This is different than that. So this is a different type of graph. So I'm going to say off to the side here, this is, let's put a different color here for that. This is in graph theory. So when we talk about quote-unquote graphs in this chapter, we're talking about this type of graph. We're not talking about the graph of an equation on the coordinate plane. We're talking about something like this instead. So I want you to draw in four actually very visible points. They shouldn't be monstrously huge, but they should definitely be visible and clearly seen. And let's call this A, B, C, and D. It should be a little bit bigger width-wise than the lines that we're drawing in between them. So I want you to draw in. That was kind of ugly looking there. Let's try to do that a little better. These don't actually need to be perfectly straight, which is kind of nice because I'm not doing this perfectly straight here, but I'm trying my best freehand here. Okay, so let's start with something like that, and I'm also going to have something like this. And that right there, that is not a tumor. Thank you, Arnold. It's not a tumor. My Arnold impression is needing some work, but it is not a tumor. Thank you. No, it's not. We'll talk about what that is in a second. So right here in graph theory, something like this is called an edge. And this would be edge A, B. Or, just like in geometry, we can switch the order of the letters with segments, with arcs, with other certain things, with lines. We can switch the order of the letters here. We could also say this is edge BA instead of AB. So either way would work with that, but let's connect that here, and we'll make another little note. Let's use this different color that we have here. Excuse me. Hopefully my voice doesn't give out here. Pardon me, I'm getting over being sick over this past weekend here. So these don't have to be drawn straight. I've had a sore throat past couple days, but feeling a little better now. So these don't have to be drawn straight. Okay, so the edges, they don't have to be drawn perfectly straight. You might see them curved a little bit. I could add another edge right here. I'm not going to do that, but I could add another one here. I could add another one here, just like we saw with, that's what I wanted to go here to here. We can have all kinds of edges coming out of the same, what are these called? These points, these are called a vertex, singular, or vertices, plural. So this right here is vertex B. That would be vertex B right there. And if you are using or talking about more than one vertex, you call that vertices. So that's vertex B. Right here, you might think, oh, that's a point where they cross, that's got to be a vertex as well. But right here, no. Be careful. You might see a lot of this going on. We can see that going on here all over the place. All these edges are crossing each other, but that's not a vertex right there. That's not a vertex right there. Just because the edges cross doesn't mean that that's actually a vertex. So this right here is, I think it's an important point to make here, not a vertex. That is not a vertex, not an. Let's use proper grammar, Mr. Wagner. Thank you. You're welcome. Just because I teach math doesn't mean I want you to learn poor English from me. I might have even said that poorly English-wise. Okay, so there is no point drawn. There's no actual dot drawn in there. Oh my gosh. Yeah, this is going to be a hard one for my voice to make it through. Still feeling the effects of getting over that sore throat. But right here, the last thing I want to talk about here, this is something you might see quite often where something will loop back to itself. It's actually what it's called. It's called a loop. So this would be loop C we would call it, because it starts at C, goes around and goes right back to C. This is edge AB because it starts at A and goes to B, or you could say it's edge BA because it starts at B and goes to A. So here's four of our new terms, or three of our new terms, edge, vertex, and loop, and we can see also what something that is not a vertex is. Also, we're seeing what a graph is in graph theory. So that's a lot of our new vocabulary here. Looks like we've made it to here already. I'm not crossing off loop. There we go. We made it to that point already. So we know what all these things are. We're going to talk about the rest of these things as we continue here. Okay, so example 1. This is probably the most famous problem in graph theory. This is how it all began, or this is where this branch of mathematics really got its start here. So it's called the Koenigsberg. I'm not sure if I'm pronouncing that exactly right, but that's how I'm going to say it here. Koenigsberg bridge problem. So this is a very, very famous problem in graph theory. This problem dates back to the 18th century in this East Prussian town, and there was this is a map of Koenigsberg. There was this island here, and there's another island here. These neon green things here are bridges connecting these pieces of land and kind of where the river is flowing, or different parts of the river are flowing. And so we're going to first represent this with a slightly more simplified version of this that in graph theory would be equivalent to what we see here. It's not going to look exactly like this, but this is basically what we have here. So I want you to draw a picture off to the side. We'll split this up into two parts. This graph, this is going to be the graph of that. This is going to be the rough map of that. So this will be, I'll call it the rough map over here. So right here, this is the land. Got a piece of land here. That's like this part right here. And then we've got another large piece of land over here. This is a simplified version again. So that's this part right here. So I've got this part represented down here. This is some more land. Got this part represented here. And then, so we've got this river flowing through here, and we've got an island. This is the way your book draws it. This is more closely looking like what your book has. We've got two islands here. So that's this island here, and that's this island right here. I know these are smaller than what you see here in the map, but this is a rough version of the same thing. And so you've got two bridges. That's right here, and you've got two more bridges right there and right there. So I'm going to draw in those bridges. And I'm trying to write sideways. This is not working too well on my device that I have, but I'm doing the best I can. These are all bridges. Let's just label those. And writing sideways, interesting. Okay, there we go. This is an island. And this is an island. And there's a bridge connecting the two islands right there. That's this one right here. So let's label that. And then there's a bridge here and here connecting this large piece of land to this island. Ugh. I'm trying. This is rough. Okay, bridge, and there's one more bridge down here. Okay, so we've got 7 bridges in total. We've got these 2 large masses of land and these 2 other small masses of land. But as a graph, how can we represent this as a graph? So let's say represented as a graph. Let's put that here. So I've got, let's use our different color for this to kind of shade in around this. So we've got all this land here. This is my land, some more land. It's an island. Island here. And some more land. So the red parts here represent vertices. So this is somewhere where you can start. The bridges are going to be my edges. And so I've got this piece of land here, and let's use our different color as well to label these things. Let's call this block of land, or this mass of land. That will be land, or part A. This part is going to be B. This is going to be C. And this is going to be D down here. Okay, so if I label those things here, I've got A. I'm going to have B and C represented by vertices, and another vertex for D. So these are my land masses, and I can connect them with bridges, which are going to be represented by the edges here. So I've got 2 bridges, 2 edges connecting A to B, right here and right here. I've also got 2 bridges, 2 edges connecting B to D. So it looks like this and this. I've got 1 edge connecting B to C, 1 bridge, and I've got 1 connecting D to C and A to C. Could I draw these curved if I wanted to? Sure. Could I have drawn these straight if I wanted to? Sure. Either way would work. So I'm going to go curved here. Ugh. Excuse me. Hopefully you'll be able to hear me actually tell what I'm saying this whole lesson. You got the map, the rough map here, and then represented as a graph what it looks like here. This is the original map. There's a guy, we talked about him a while back. I think that was with our set theory chapter. I'm trying to remember if that's right. I hope that's right. But there was a guy named Leonhard Euler, and Euler was the first one to really dig into graph theory and to start that whole process, or that branch of mathematics. And he came up with some different theorems, some different ideas about graph theory, and other people expanded on his ideas later as it continued to become a more valuable branch of mathematics, a more applicable branch to mathematics. More and more applications are still being found today with that. So let's move on. We've represented that with a graph. We are going to return to that Königsberg Bridge problem in the next lesson, but for right now, we're just going to be good with that. So on this next one, I don't have to have you, I'm not going to have you draw the map here. I was thinking about it, but I'm going to just say I'm going to get rid of these ones, so I'm not going to have us do anything with Kentucky, West Virginia, South Carolina, North Carolina. So pretend these aren't here. This is the Southeast United States. If you're a football fan, at least right now when I'm making this video, the Powerhouse Conference is the Southeastern Conference. We've got most of the national championships have been going to schools from these states. Most recently, I'm crossing off South Carolina. That would be included in the SEC, and Kentucky. If you're a football fan, you would know that. If you really like college football. If you don't like college football, well, now you know. But well, let's see what we got here. So I'm gonna take this, and you know what? Yeah, we're gonna at least outline this. So I want you to do the best you can with this. And so this is going to be, let's say this is the problem. Construct a graph to show the states that have a common border on the map below. So I'm changing my mind on that. Sorry, you're gonna have to draw the states in as best you can, because I'm saying that because otherwise it's gonna be really not that valuable looking at your notes, because we won't be able to say what came from what, or how did the graph actually form. So this is the graph theory version. This is going to be represented as a graph on the right, and we'll have our map, the original map, on the left. So you can pause this if you need to, but I'm going to outline the states, and then I'm going to put that over here. I get to cheat. You don't get to cheat. You're just going to have to draw it as best you can. I'm not going to be real picky about how good your drawing is. Just try to make the states look like they do here as best you can, and trace that out on your map there. So I'm just this really good artist there. That was amazing how that was just really well done. Nice job, Mr. Wagner. Okay, so you can pause the video if you need to, and just make that as best you can. We'll label these states like they are here. So this is Arkansas, Louisiana, a little geography lesson here, Mississippi, Alabama, Tennessee, Georgia, and Florida down here. And then we're going to represent these states with vertices, and each border that they have in common will be an edge. And so we've got Tennessee sharing borders with 4 different states that are showing up here. It actually shares a border with, I think it's 9 states. I think it's the state with the most shared borders. But that would be Missouri right here. We got Kentucky and all that. But we're just doing this smaller section of it, just as we start to get used to this. So this will be Tennessee. I'm going to just basically roughly put them where the centers of the states would be. They don't have to be drawn in these same exact places. As long as you have a dot representing each and an edge connecting each one of them, you'll be fine. It'll be just fine. So these just need to be drawn in somewhere, trying to just put them relatively matching up to where they are there. This is Georgia, Florida right there, and then I need to figure out how many borders are shared here. So Tennessee, it shares a border with Georgia, Alabama, Mississippi, and Arkansas. So I should have an edge connecting Tennessee to each one of those states. Do these have to be curved? No, they could be straight. This is just one way to represent it. Let's check out Arkansas next. It's got a border in common with Tennessee. We've already drawn that one in though. Also Mississippi and Louisiana. And then Louisiana just with Mississippi and Arkansas. Mississippi, we've already got Arkansas and Louisiana. We've got Alabama that needs to be drawn in as well. Alabama with Tennessee, Georgia, and Florida. So we've got connections there. And then Georgia just missing the connection it has with Florida. So as a graph, make sure these vertices are clear, that those are actual points where you could be stopping and starting at. And so we're not really doing much with that in terms of applications of graph theory. Right now we're just getting used to how to create the graphs in the first place. We're going to do applications as we do our next lessons in this chapter. So let's continue with a third example. I thought this was a really cool house. If you're interested in architecture or engineering, you might be looking at floor plans someday. Or if you're interested in construction, maybe you're interested in doing the actual manual labor part of it, where you actually construct a building, you'll definitely need to know how to read floor plans. So this is going to be a very rough floor plan, but let's construct a graph to represent the floor plan. That's an R. There we go, the floor plan below. And I want you to also write this in. Assume that spaces in the lines represents doorways or passageways. You'll see what I mean by that in a moment. Okay, so let's put our floor plan off to the left and our graph, represented as a graph, off to the right here. And so hopefully you are using pencil. If you've been using pen, let's get a pencil out at this point to do this part, because I'm going to put it all in here first without any spaces in the lines, and then I'm going to erase certain parts where our doorways or passageways will be. So I want you to make a rectangle, fairly large rectangle. And again, this is a very rough floor plan. A real floor plan would have these walls drawn in to a very specific thickness. You'd have a scale to your drawing. Everything would be drawn to scale. And whatever you would have on the floor plan, you could use that. You could actually measure it scale-wise, and to make the construction of the building, you should be able to depend exactly on the floor plan as it is drawn to scale and construct it right from there. But we are drawing a very rough floor plan here. I would not take this one to the building site and start building based on something like this. I thought I was actually going to be an architect for a while myself, until I decided that that was not the career for me. But I still enjoy looking at floor plans, and I still enjoy architecture. I still think I'd like to design my own house someday. I think that'd be really cool. But I'm putting in now these empty spaces, or these breaks in the lines, are going to be either doorways or passageways. We're not going to draw in. You might see, don't draw this in right at this moment, but you might see on a real floor plan, you would see something like that. If there was a door, you would see a door drawn in, something like that. We're just going to leave that out for right now. So a very rough floor plan. Doesn't even have doors drawn in, okay? So these are either doors or passageways. There's going to be one there. It's going to be kind of a big one here. Another big one here. I would assume these would be then passageways instead of doorways, or maybe double doors. We're going to say there's one here and another one right here. And there's going to be an opening into this room from the outside there, opening this room to the outside, and an opening from this room to the outside. And this room needs an opening as well, so we want to be able to actually get into that room. There we go. This is going to be the guest bedroom, and this will be the master bedroom. This is going to be a bathroom. I forgot one opening here, so let's also give an opening right there. The master bedroom then has an opening to that bathroom. This is going to be, we'll call this the gallery. Most houses I don't think have galleries, but we'll call that, we'll pretend this one does. This is the dining. This is not a floor plan matching up with this house. I just like this house. I thought it was a really cool design. I would enjoy living in a house like that, very modern, chic, slick looking. This is going to be the kitchen. So we've got an entryway into the kitchen. This will be the living room. And then all the openings again representing doorways or passageways. And so let's represent each room with a vertex, and each opening can be represented with an edge. These are going to be connections between the rooms, connections between the vertices. And so I'm going to put these in their relative position. I'll say that this will be not Great Britain, but the guest bedroom. Generally, you'll see vertices with just a single letter, but you could use more than one letter. You could use a whole word if you really wanted to. Whatever would work best in the situation is really, I think, the best way to label things. And so I'm going to use, if they have two words, I'm going to use two letters here. If they just have one, I'll just use one. So this will be the dining. This will be the kitchen. Sometimes you'd see dining room, but I'll just say dining to make it a little easier. The gallery is about there. I'm just trying to put these generally in the center of the rooms that they are representing there. And we'll have a bathroom here, and the living room we'll say is LR. And so now let's connect these, not just willy-nilly wherever we feel like connecting them, but looking at the actual rooms, the actual floor plan here, and edges wherever you see a doorway or passageway. So I see a doorway or passageway connecting the guest bedroom to the gallery, but that's it. There is no connection between the guest bedroom and the dining room, no direct connection at least. So I'm not going to draw anything here, not going to draw anything between the guest bedroom and the master bedroom. It's just that to the gallery. So that's the only way to get to the guest bedroom is to start at the gallery, or to get to the gallery eventually from some other room. From the dining room, there's connections to the gallery and the kitchen. So I'm going to draw those in. From the kitchen, we have connections to the dining room. We have connections here to here to the gallery. I'm going to draw in another one here. And then there's two connections to the living room. So I'm going to draw in two edges connecting the kitchen to the living room. And then we'll take care of this one in a moment. So we'll get to that. The living room, we've already drawn that connection, so we just have to take care of this one later. There's a gallery to the bedroom or the bathroom connection. And then the master bedroom, there's a connector to the gallery and the bathroom. So now what about these parts though? Well, this is saying you could go outside and go directly to the living room from the master bedroom like that. So we could say that there would be a connection then from here to here. And we could also say that there's going to be a connection from the living room to the kitchen. We could connect there to there, living room to kitchen, another one. So that'd be a third connection. That would be represented something like that, we could say. And there would also be a connection from the kitchen to the master bedroom. You could go directly from there to there by going outside and going like that. So let's draw that in like that, and that should do it for us. Okay, so I think it'd be a good idea to label these things just for the sake of our notes here, to better understand that when we look at this again later. So let's put numbers where we see these openings. So that'll be number 1. That matches up with that one right there. This will be number 2. That's the master to gallery, so that's number 2. Let's say this is number 3. That was this big long one out to here, 3 and 4. We'll call this 3 and 4. So it's the master to the living room, and it's the master to the kitchen. And so I'll put a 3 next to that one and a 4 next to that one. Alright, and so with the dining to gallery, let's call that 5. This is number 5, edge number 5. Then the gallery to the bathroom, we'll call that 6. That's opening number 6, or edge number 6. Dining to kitchen, 7. Gallery to kitchen is 8. And then there's 2 from the kitchen to the living room, we'll call that 9 and 10. And then there's the outside one. Let's call that 11. So I think on here it'd be helpful to do something like that too. Just call that 4. We're connecting 4 to 4 there. Excuse me. This would be 3 and 11. So 3 would connect here to here, and 11 would connect there to there. Let's see, does that cover all of our bases? I think it does. Oh, no, we're missing one right here. My fault. Let's just call that number 12. That's the master to the bathroom. Okay, so that looks like I'll do that. The red stuff would not be something you would have to include on a problem like this later. This is just to help us look back at this later and see how those connections were all made, or where those all came from. So remember the original openings, that was the passageway or doorway, and then the numbers are just ways that we represent those together. So you don't necessarily have to do something like that with the numbers later on, you just have to represent it. Okay, example 4. Before we do that though, I wanted to make one more quick note. So to save us a little bit of time here on the notes, I was looking at the examples in the book, and I felt like, you know what, if you just look at this one in the book, I think we've done 3 really solid examples already. And so if you need help with 31 and 32, any of those that I might end up assigning to you in your book, so for help with those in lesson 14.1, you should see example 4 on pages 829 to 830. Okay, let's move on then to a 4th example. And this one I'm going to draw a graph right away. So this is what our graph will look like to start. So this time we're not starting with a picture or a map. We're starting with the graph itself. And then I just want you to connect those just like you see here. I'll continue this way. And then, oh, one of those guys. And thank you, Arnold, for the reminder. Yes, that is not a tumor, that is a loop. So let's see what we got here. Here's the question, or here's the problem you need to decide on in the graph above. Determine the degree of each vertex. So we're learning about the degrees and what that means. So the degree of each vertex and whether it is even or odd. So even or odd vertices, vertexes, no, vertices is how we say that. So I was tempted to say vertexes. It's vertices. Thank you. Thank you. Get it right, Mr. Wagner. Okay. I'll try. So the vertex, the degree here, and whether it's even or odd, I'm going to put that here. Just going to arrange my thoughts in a table. Makes it a little easier to keep things all lined up, keep things all straight. So we've got 6 vertices up here, A through F, and the degree. What is the degree? How do we determine what a degree is? So let's put that off to the side here. Different color at this point, and off to the side. Let's say how that is determined. And so this one, how is the degree determined? It's determined by the number of edges connected to a vertex. So if we look here, vertex A, it's got 1, 2 different edges emanating out of the vertex, and so we've got a degree of 2 right there. If we look at B, there's 1, 2, 3 different vertices emanating or coming out of vertex B, so that would have a degree of 3. Likewise, C has 3, 1, 2, 3. D we'll come back to in a second. E has 3, sorry. And F has 3 as well. I was thinking of D. D, how are we going to determine that? Because there's one edge here, and this is really one edge, but it's a loop. And so do we count loops as 1 or 2? Because it's coming out there, but then it's coming right back in there. So think of your degrees with loops like this. It's just how many things actually come out of there. So how many things start to come out. Just count those numbers of things. I just kind of go around in a circle until I count them all. So this is 1, 2, 3, 4 different parts shooting out or jutting out, emanating from each, or from the degree, from degree D right there. So here, as I go around in a circle, 1, 2, 3, that gets them all here. 1, 2, 3, that gets them all here. 1, 2, that gets them all with A, and so on. So Let's make a little note of that. With that one that loops, will count as 2 edges. Will count as 2 edges when determining degrees. And then even or odd, what do we have here? So just look at the degree number. If the degree is even, that means it's an even vertex. If the degree is odd, that means it's an odd vertex. So it's as simple as that to determine if it's even or odd. 2 and 4 are both even numbers. 3s, those are all odd numbers. And so the rest of these would be odd right there. And so let's just make a little note of that right here. Hopefully none of this stuff has been too hard so far. I don't think it's hard things to grasp, just a lot of new concepts, so a lot of new words or words that we've heard before that have different meanings in another context but have this meaning within the graph theory context. So these are based on whether the degree is even or odd. Odd, there we go. And now for some definitions, and then we'll check out a couple of final examples to end the lesson from there. So a path is a sequence of adjacent vertices And I would say, as you're copying these definitions down, this is the part to be especially focused on because these ideas are going to show up again in the next few lessons here. This idea of a path, an idea of a circuit, and how that relates to what we'll see later on in this chapter. So a sequence of adjacent vertices and the edges connecting them. And we're going to see an example of a path in a moment, so if you just read that and you're like, I have no idea what you are talking about, you need to stop talking, Mr. Weiger. No, I need to keep talking so that you can hopefully get a better idea of what we're talking about here. So a circuit, but I'll draw pictures, okay? So we'll get there. We'll draw a picture. Let's just define these things first. A circuit is a path. So it's a special type of path. In other words, a circuit is a path that begins and ends at the same vertex. And then let's make a little quick note here that a circuit, since it is a path, a circuit, it's a special type of path. A circuit is always a path. But a path doesn't have to begin and end at the same vertex, so a path is not always a vertex. Not, that's a T, I promise. There we go. Not always a vertex. So let's just draw a couple of quick graphs here. This is kind of a pseudo example, not really a full-fledged example. I just am trying to show you pictorially what that would look like. So I'm taking my graph from here. I'm just going to draw the same graph but without a loop on D. So let's call this the graph here. Call the points like you see them here. See them labeled. Label them just like that for me. And so if I were to say draw path, and then we always separate the vertices with commas. I think this is especially important to note that because sometimes these vertices are more than one letter. Sometimes they could be a whole word. So we're going to say path A, comma B, comma F, comma C. And so what would that look like in this picture? Different color time. Let's connect those and see what that looks like. So that would be, sometimes you'll see it drawn like this where it's just kind of curving around. So A to B, and then B to F, and then I actually meant to insert another letter in there. I'm sorry. This should have been E and then C. So E, comma, C. There we go. Because that's a good point to bring up there. If I said F to C, there's no actual edge connecting F to C, so that's not a possible path. A path has to connect. It has a sequence. It is a sequence of adjacent vertices and edges connecting them. Since there's nothing connecting F to C, I couldn't do that. So I did that on purpose. Right, you did, Mr. Wagner. I really... It's not working? No? You don't think I did that on purpose? I guess that will be for you to figure out. But anyways, this would be path A, B, F, E, C. It's just connecting those adjacent vertices in that path or in that order. Let's draw another graph over here to show a circuit instead. And so this one I'm going to go with something that looks like this. So I'm going to connect that here, that here. This is where the different color will come in, especially helpful because it's kind of hard to tell what's originally there and then what the path is from there. I'll show you another way that we'll use, at least as our class. You might not see it in the book like this, but another way we might use to represent paths and circuits instead of drawing in an extra whole part here. I'll show you later on in this chapter. Later on in this lesson, no, but later on in this chapter we'll have a different way to look at it too. But let's call this O, G, R, E right here, and S. Aha, that's where this comes into play. Hello, Shrek and family. Excuse me. So this, let's say we want to draw circuit O, comma, E, G, R, E. If I stop right there, it wouldn't be a circuit because it's got to begin and end at the same letter. So it has to end at the one you started at. So let's say I told you to draw that circuit. So it almost looks like Oreo with an E and G inserted in there. But starting at O, first going to E, so we'd be following along this edge. Let's draw that in. So we're going from there this way, and then to G. So we're going then to there, and then to R. So we're going like that, and then to E, right there, and then back to O. And so I could come back that way. So a circuit, if you think of an electrical circuit or something like that, the circuit always connects back to itself. It always goes back to where you started. So we got that circuit going. You could keep that same path going, and you would continually keep going through that path through that circuit. But here, if you went the path and did that once, you'd have to jump back to A. There's no connector directly from C to A there, so that's not a circuit. It's got to end. This one would have to end back at A. This one does not do that. So this is a path, and this is a circuit. This is still a path over here, but it's a special type of path because it begins and ends at the same vertex. Therefore, it's a circuit. Okay, so that's the difference between those two. And now let's check out another definition, both with words and with a picture. So a graph is connected. Call it a connected graph. In other words, a graph is connected if for any two, I'm going to double underline two, or I'm going to underline double underline any, I'm sorry. There we go. For any two vertices, not just one pair, but any two vertices that you come up with. So with any two vertices, in the graph there is a path that connects them. So we're going to have some disconnected points here in these examples of disconnected graphs. Every graph we've drawn so far has been a connected graph. There's no points just hanging out by themselves, or there's no disconnected part where you can't get from one point to another point by going along some type of edge. And you'll see what I mean by all that in a moment. But examples of disconnected graphs here. So this is kind of like a pseudo example, or just one that's helping us see how this definition works out. I'm going to draw these three kind of colored blob areas just to show you that this is one problem, this is another problem, this is another problem, third problem here. So let's say you had something like this. These are vertices A, B, and C. And let's say there was two edges here and here, and that was it. This is a one example. Why is this disconnected? Well, there's no connection between A and B or A and C. If I drew one little piece in, one little edge in here, that would make it connected. There would be a way to get from C to A. You would just have to go through B first, but there's no way to get from A to C. There's no way to get from A to B. There's no way to get in between those parts there. So that's disconnected. You might see something like this, where you've got a connected part here and a connected part here. This is supposed to be G, there we go, G, D, E, and F. So we've got a connected part here and a connected part here, but this is all within the same example I'm saying, so this is kind of like part 2 of this. There's no connection, there's no way to get from D, E, or F over to G and H. There's no edges connecting those at all. If I just made one little edge here, then there would be a way to get there from D. I would have to go through F to G, or from E through F to G, or from F straight to G. But there's nothing there, there's nothing there, and so these are disconnected. This is a disconnected graph. And then this one, you might say, what are you talking about? That's totally connected, Mr. Wagner. But think back to what we talked about before. I'm going to go back to the very first slide here, and remember that if they cross, just because the edges cross does not mean that you have a vertex. There is no vertex unless there's an actual physical point drawn in there. So there's nothing connecting J and K to O and E. Just because they overlap doesn't mean that they're excuse me, that they are connected here. So right here, these are, or this is an example of a disconnected graph because there's no path connecting J and K. I should say J or K rather. So connecting J or K to O or E. Okay, so that's why this one doesn't work up here. And almost there, last little part here, I'm going to move this down just a little bit, and I'm going to include one more definition here. So a bridge. Now this is not the type of bridge we had in our first example. So this was an actual physical bridge that was built over water. Now we're going to have a different way to think about a bridge. This is the way I want you to think about it for the rest of this chapter. A bridge is not something physical you walk across. A bridge is, in graph theory, is an edge that, if removed, from a connected graph, I should include that, if removed from a connected graph, would create a disconnected graph. And so our final example, last thing we're going to do here, identify any bridges in the graphs below. So I'm going to do 3 little different parts here. I'll just split it up like this time. So let's use our different color for that. This is a kind of a 3-in-1 example here. So 3 real quick examples. That's connected there. Okay, and this is going to be 4 vertices here. That'll be B, O, Y, and S. And so we've got one more edge there. And then down here, let's put what our bridges would be. So the bridges for this one, and this one as we go through this. So this one, if I got rid of this edge, everything would still be connected. There would still be a way to get from any point to any other point. That's another good way to think of it, I think. As long as you can get from any point you start with to any other point on the graph by going through some path connecting those points, then you're good. But if you got rid of this edge right here, there would be no way to get to S from any of the other points, or to any of the other points. And so a bridge here, edge OS or SO would be a bridge. So bridge, or edge OS is a bridge. If we got rid of that, if we remove that, don't actually erase this right now, I'm just showing you what would happen if we did. So if we got rid of that, there's no way to get from S to any one of those other spots. So that is a bridge because of that. Let's say we had, let's draw the vertices roughly of a regular pentagon, and let's connect them in this way. And one more, there we go. Let's say we had boys in the first one, we'll have girls in the second one. And so is there a bridge here? Is there any bridges to go with this one? So right here was edge OS. With this one, I could get rid of this one. They'd all still be connected. There'd still be a way to get from one point to any other point on the graph. Same with this one, same with this one, same with this one, but not with this one. So this one would be edge IR or RI. So we'll call it RI. Edge RI would be a bridge in that one. And let's do one more here, like this. Okay, so let's call this O, G, R, and E. That's who's hiding over here. They're back. The ogres are back. And there's boy ogres and girl ogres. It almost sounded like I said boogers. And boy ogres. If you say that together, boigers, yeah, it kind of sounds like it. Gross. Anyways, edges, there's going to be more than one here. If I got rid of this edge right here, O, there's no way to get to the other points if I got rid of OR. If I got rid of EG, the same thing. Same idea. There's no way to get to E to any of these other points, or from E to any of these other points. So EG would be another edge that is a bridge. And if I got rid of GR, that's actually the only other edge that's there. But if I got rid of that, then there's no way to get from G to E over to either O or R. And so every single edge in this one happens to also be a bridge. And so those would be our answers for that one. As needed, go back and review any of these examples. Make sure you really have a solid understanding of this stuff, what each word means. We're going to need solid understandings of each definition that we saw here to be able to be successful in this chapter. Don't think it's a hard first lesson, but a lot of new stuff, so review as you need to. And one more thing here. I was going to make this a little bigger. This made me very sad. So I thought, oh, that was a good joke, and joke that was right here, J-O-K-N-E. And then I read the fine print here. That is not true. Disappointing.